Okay, class, picking up where we left off at, the answer was 0.05%. That was the final answer because you were supposed to take the actual value minus the estimated value, which we did here, and divide it by the estimated value. And that gave us a 0.0047. And we converted that to a percent, which is approximately 0.05%. Okay, now we scroll on to problem 18. It says you have been offered two jobs. One job has a starting salary of $45,000 with a 2.5% raise each year, and the other job has a starting salary of $42,000 with a 3.5% raise each year. How much money will you earn at each salary the sixth year? Okay, now I took the liberty in filling in these blanks from your review packet. Now, what you have to realize is when you're talking about raises on a job, that's the same thing as compound interest. So we did this according to the compound interest formula. So we did the 45,000 times the 0.025%, and then we got that value, added it, and then got the new value and still multiplied it to the 0.025%. And just to visually show it to you, we took 45,000 times 0.025, and that gave us the 1,125, which we added to the 45,000. Then we had to take our new salary and multiply by the same 0.025, and that would give us the new interest, and we would keep going from there. And we did the same thing for the 42,000, but we had to do about a 3.5%. Now, it asks us here, it told us first to complete the table, and then it says B, compare your total earnings for the 5 years for each job offer. Which job provides the highest total earnings after 5 years, and how much more are the earnings? Now, one thing you have to realize is year one, you kept the same salary. That is why we had to go to year 6 to go over the 5 years. So now when we add up all of those values from the salary of $45,000, we ended up with a total of $287,448.16. And then for the 42,000, we ended up with $275,106.40. Now we're supposed to subtract these values. And when we subtract these values, we come up with $12,341.76. That's more was earned. In the $45,000 a year job. Okay, now it says describe the correlation and its strength between the variables in the graph below. Okay, now it says here graduate students GPA and GMAT score. Okay, now we have this scatter plot here. Now we know a line can go possibly here. So what I did here, I took the liberty of adding in this line here so you could get a visual representation of what the line would look like. Okay, so it says describe the correlation and its strength between the variables in a graph. It should be the graph below. Okay, now if you look here, most of these dots here or these points here are very close together. So the strength is basically moderate to strong. Because we know for it to be strong, it'll be even closer as a line. Okay, now the correlation. If you notice, these points are going in a positive direction because they're going up. So the correlation is a positive correlation. Okay, now we go here to problem 20. It says determine whether the following data sets are linear, exponential, or neither. Show your work to justify your answer. Okay, now we basically could do this a few ways. We could put this in a calculator and then have the calculator work it out for us, and then we could see whether or not it's more linear, exponential, or neither. Okay, but this is what I want to do. Let's take a look at the calculator. We could go to Stat, we can go to Enter, we can clear this out. We can go to our table. We have 20, 25, 30, 35, 40. And then we'll go over here and type in the Y value, 120, 180, 270, 405, and 607.5. Okay, so we put in these values. Now what we would do is this here. First, we have to make sure that our stat plot is on. So we'll press second and Y equals. And if your stat plot is not on, your plot one is not on, you'll press enter, and then you'll just press enter on. Okay, now we need to get off. Well, let's go to Y equals and clear out any equation you may have in here. So now we'll press zoom, and we will go down here to where it says zoom stat, which is number 9. And if you look here, this looks linear. Well, actually it looks exponential, not linear. You notice here this curve is going more exponential than it is linear. So your answer here would be exponential. Okay, now for B. Now we will go here and we will go to the stat plot again. Press enter. We need to clear out L2. Then we'll go to L1 and clear out L1. And then we will type in these values. We have 125, 130, 140, 145, and 160. Okay, next we will have 325, 350, 400, 425, and 500. Okay, now we'll go back to zoom. We'll go down here to the stat plot, which is zoom stat, and we look here. Okay, now it looks linear, but we have to do one more test. We have to take a look here because we know with a linear equation that the slope and the change in x and change in y must be consistent. So here from 125 to 30 is 5. From 125 to 130 is 5. From 130 to 140 is 10. 140 to 145 is 5. And 145 to 160 is 15. Now if we go by fives, well 125 to 130 is 5. Now if we have 135 in here, we know 130 to 135 would be 5. And 130 to 140 would be 10. So the x values are consistent. Now we go here to the y value. 325 to 350, that's a difference of 25. From 350 to 400, that'll be 50. And then 400 to 425 would be 25. And 425 to 500 would be 75. This is also consistent. So basically, this would be linear. Okay, now I did make one little error on 20A. I was supposed to do the same thing we did for B here to make sure everything was consistent in addition to looking at that graph. This is a difference of 5, this is a difference of 5, difference of 5, and a difference of 5. because we had to add 5 for all of these. Now we look here to go from 120 to 180 is 60. To go from 180 to 270 is 90. To go from 270 to 405 is 135. And to go from 405 to 607.5 would be 202.5. Okay, now, if we do the change here, the change, we would take the change here from 120 to 180 is 60. We would take 60 divided by the previous number. 60 divided by 120 is 0.5. And then we would do here with the 90, from 180 to 270 is 90. 90 divided by 180 is 0.5, and so on. You still will get 0.5 all the way down. So A is exponential. All right, now we go down here to 21. It says in 2000, the population of mice in East Fremont is 200,000 and growing, as the table below indicates. Okay, I took the liberty in filling out these values here. The actual growth was basically taking the current year, which here would be 2001, minus the previous year, and then we would do the same thing. Current minus previous, and so on. That gave us the actual growth. Now to find out the percent of growth, we would take this value and divide it by the previous year's population. So you take 4,000 divided by 200,000. And that gives you 0.2. And then you could take 4,080 divided by the previous year, which would be 204. 204,000, and that gave you 0.2, and so on. So it still will give you a consistent rate of growth of 0.02. Okay, now A told us to complete the table, which we did here. Okay, B, was the growth of mice linear or exponential? And we know this growth was exponential. And it's exponential because the percent of growth was approximately the same each year. Okay, now it says here, using the growth rate, determine the expected population in mice in 2010. Now remember, we started off in the year 2000. So that's a 10-year difference here. So we have to write out the formula. So we started off with 200,000. In 2000, our population was 200,000. So we know we're using a formula, and I should have wrote that down first, so let me correct this. We're using this formula here. We know we're using y equals a times b to the x, and y is equal to a is the initial value, which was 200,000. B is the growth rate. Now we know that it grew like 2% each year, so it'll be 1.02, because remember we got to add 100% to that. And the years is 10, so we'll take it to the 10th power. And our answer, once we round to the nearest whole number, would be 243,000. 243,799. And that will be our final answer. Okay, class, with problem 23, I told you all to cross out 23 and put 22. So it will match up with your answer key.